Test Site has been our nation's principal nuclear explosives testing area since it was established in 1950. Since August 1962, all nuclear tests have been conducted underground. The continuing weapons testing program at the Nevada Test Site is vital to our nation's security. Headquartered in Washington, D.C., the Energy Research and Development Administration, or ERDA, has responsibility by law for developing, testing, and providing nuclear weapons and explosives for peaceful purposes. Development of new nuclear devices originates in ERDA contractor laboratories, where scientists generate ideas to meet military requirements for new or improved weapons. Nuclear tests are essential to the evolution of weapon technology. Both the theoretical scientist and the hardware designer require detailed information on the performance of each step in the development of a weapon. As many as 20 separate experiments or test detonations may be required before a completed design emerges. Work is also performed on the design and development of non-nuclear components, and many studies are made on the effects of nuclear explosions on weapon systems. Sophisticated device diagnostics, arming and firing hardware, and new methods for studying and understanding explosion containment and ground motion are all a part of the nuclear weapons testing program. Nuclear explosives for peaceful purposes also have been tested at the site. The Department of Defense develops specially designed tests to find out, for example, how nuclear detonations might affect our retaliatory defense systems, how communication systems would be affected by radiation, or how hardened structures would stand up under attack. Prototypes for all warheads of recently developed nuclear defense systems in the United States arsenal have been tested in Nevada. These include the Poseidon submarine missile, the Minuteman II, and many others. These programs are managed by the ERDA's Nevada Operations Office in Las Vegas, the nearest city to the Nevada Test Site. The manager of the Nevada Operations Office is responsible for all test site activity.
Our national security requires that the military services be provided with modern nuclear weapons to meet the strategic and tactical requirements in this ever-changing world situation. Testing of nuclear devices plays a vital role in the development and reliability of these nuclear weapons. These tests provide scientific information which cannot be gathered in any other way. The Limited Nuclear Test Ban Treaty, signed in 1963, restricts nuclear tests to those which can be conducted underground and which will not cause radioactive debris to be present outside the territorial limits of the country under whose jurisdiction or control the tests are conducted. Underground tests of nuclear devices do not just happen. Each has a specific purpose and is a complicated and expensive undertaking. Long before the tests begin, panels of consultants and unbiased experts must determine that the possible damage to the public, to public property, and to the environment are negligible. No chances are taken with public safety. Proposals for nuclear tests are reviewed by ERDA's Division of Military Application in Washington, D.C., and are approved by the administrator himself, by a special committee of undersecretaries, and finally, by the Office of the President. We work very hard at conducting our tests in a manner which will ensure complete public safety.
During and after the time when plans for an underground nuclear test are being completed and necessary approvals are being received, a containment evaluation panel makes expert and careful reviews to see that all appropriate steps have been taken to assure that the radioactivity produced by the test will remain underground and not be released to the atmosphere. The Nevada Operations Office contains divisions of physical sciences and bioenvironmental sciences. These groups continuously study all potential effects of the entire testing program on our environment. Results of an extensive sampling program involving geological studies and bioenvironmental sampling are used to predict, document, and evaluate the effects of nuclear tests. On high-rise buildings in Las Vegas, detailed structural engineering studies have provided information on how tall buildings react to ground motion. Seismic monitoring of buildings has verified the predictions by structural engineers that no significant offsite damage will result from detonations with yields of up to 1,000 kilotons. At the higher yields, the ground motions generated are clearly felt as far away as Las Vegas. The Environmental Protection Agency acts as an advisor and provides technical assistance to ERDA in matters concerning public health and safety. Areas surrounding the Nevada test site are monitored by the EPA in a long-range program which documents radiation in the environment. Some of the test site neighbors in the nearby region cooperate in this program by wearing radiation measurement devices. These are collected regularly and compared with radiation data obtained through other monitoring programs. Samples of milk, water, vegetation, and soil are collected from areas outside the test site and analyzed at the EPA's Environmental Monitoring and Support Laboratory, located on the campus of the University of Nevada at Las Vegas. Results of these studies are summarized in the Environmental Impact Statement for Underground Nuclear Testing at the Nevada Test Site. This statement and many of the reports resulting from the safety and environmental studies are available in ERDA's technical library. Thousands of Las Vegans work in the city and at the Nevada test site for ERDA and its contractors and for associated government agencies. But Las Vegas is far better known for its fabulous casinos. This is the tourist Las Vegas. At dawn, when the crowds begin to thin in the casinos and the tourists' long night is ending, a long day is just beginning for the thousands of permanent residents of Las Vegas who work at the Nevada test site. They are preparing for the ride through 65 monotonous miles of desert to the headquarters of Nevada test site operations at Mercury, Nevada. Another 25 to 50 miles must be traveled by those working in the test areas to the north. Mercury is an administrative headquarters and supply base for ERDA contractors and other agencies involved in Nevada test site operations. Beyond Mercury lie the main test areas of Yucca Flat, Rainier Mesa, and Paiute Mesa. The control point is the nerve center and command headquarters for most of the testing activities. It sits in a desert mountain saddle overlooking Frenchman and Yucca Flats. The location for most of the underground detonations at the Nevada test site is Yucca Flat, a valley roughly 10 by 20 miles, extending north from the control point. Tests up to about 300 kilotons in yield have been conducted beneath Yucca Flat. Larger tests up to 1,000 kilotons have been conducted beneath Paiute Mesa, a 170 square mile area in the extreme northwestern part of the test site. The location and geology of this rugged rolling mesa made practical the testing of nuclear explosives at depths down to more than 4,500 feet, with small chance of ground motion causing damage off-site. Some early underground tests in 1957 and 1958 were conducted at the end of horizontal mine drifts in soft volcanic rock. In recent years, tunnels in Rainier Mesa have been used only for events requiring elaborate instrumentation for Department of Defense effects-type experiments. Since 1957, large diameter drilled vertical holes have been used for most underground nuclear explosive experiments at the Nevada test site. Depending on the design size or yield of the explosion, a hole is drilled to a depth calculated to contain the explosive energy in the earth and to minimize the chance of venting or escape of radioactive debris. Specialized drilling equipment and techniques have been developed at the Nevada test site, which have made possible the drilling and casing of holes more than a mile deep and up to 12 feet in diameter. The drilling is so precise that usually there is a clear line of sight all the way to the bottom. The hole has to be so straight that a test canister containing the nuclear explosive and measuring instrument package, sometimes 200 feet or more long, can be lowered without binding. When the hole is ready, a dummy package, slightly larger than the test canister, is lowered to the bottom of the shaft to make sure that the canister will not stick or bind while being emplaced. Portable buildings are moved into the test area. Inside these buildings, final preparations of the nuclear explosive and instrumentation canister are carried out under strict security regulations. Miles of cable are strung for transmission of signals from the canister to nearby recording stations. Signals are transmitted by microwave relay to and from the control point. When preparations are complete, the canister containing the nuclear explosive and instruments for determining results of the test is lowered into the shaft. Nuclear explosives are tested in holes ranging from 600 feet to more than a mile deep. Major advances have been made by the laboratories for obtaining essential information from tests conducted underground. After the nuclear explosive is in place, the shaft is filled with sand, gravel, and plugs of concrete or plastic. This stemming or backfilling completes the emplacement, which has been coordinated closely with simultaneous test preparations in the recording stations and at the control point. Control rooms house the complex timing and firing systems which transmit electrical signals by microwave and cable to detonate the nuclear explosive and to turn on and off recording instruments. Scientific data from the experiments are recorded at the control point and in the field recording stations near Ground Zero. Dry or trial runs to verify proper installation of the circuitry are made, beginning with installations of the first units. All instrumentation must function properly. Each of the programmed actions must occur in precisely the right sequence and at exactly the correct instant, or the run is repeated. 6 to 10 dry runs for an event are normal. There may be 15 or more. Every test which might cause enough ground motion to have potential adverse effects outside the boundaries of the test site is announced publicly in advance. Monitors from the Environmental Protection Agency visit remote locations around the test site and advise area residents of safety procedures to be followed at the time of the test. Particular attention is given to people who may be working in mines or other potentially hazardous locations. The strongest emphasis is placed on radiation safety of the public and on-site workers. Monitors are directed from the control point to positions where they can take protective action if necessary in the unlikely event of radiation being detected off-site. Only rarely have small amounts of radioactivity been released. The levels measured off-site have been well below those permitted by existing radiation guides.
Net control, this is 256. The air samplers and gamma rate recorders at Alamo and Hyco are in operation, and I am standing by at Crystal Springs.
140, on location at Death Valley Junction.
Wind and weather predictions are vital because in case of an accidental release of radioactivity, downwind radiation levels must be predicted for inhabited places and highways. Weather conditions are monitored throughout the testing period by the Air Resources Laboratory of the National Oceanic and Atmospheric Administration.
Ball from Death Valley Junction. Surface winds 1535, 1770, minute 7, 531.
Finally, preparations are complete. The explosive is in place. The recording instruments and timing and firing systems are ready. On the afternoon or evening before the day of the test, a formal briefing is held to determine technical readiness to proceed. Members of the Test Controllers Advisory Panel, who are experts in the fields of nuclear weapons, meteorology, radiation, and medicine, receive a complete briefing on the technical aspects of the test. This is followed by a detailed study of the weather and public safety considerations. If a leak from the test might conceivably result in unacceptable levels of radiation at populated places, the test is postponed. A review is made of the location of all persons and domestic animals living in areas which might be affected by any release of radiation, however unlikely. Plans are made by the Environmental Protection Agency to ensure their safety. Miles out in the field, a security sweep by ground patrols and helicopter confirms that all personnel not connected with the test have been evacuated from the forward areas of the test site. At the main assembly point, radiation safety personnel arrive, along with men who will be engaged in re-entry and post-test operations. The test location is deserted. Once the decision is made to proceed with the test, the final party to leave the area arms the device to make it capable of producing a nuclear explosion. Special safety procedures ensure that the device cannot be detonated until it is armed and the necessary coded signals are received from the control point. Radiation detectors surround the test area. The instruments are connected to a central room from which any radiation readings after the test are automatically transmitted to the command room. Recording stations are ready to receive the signals from the instruments in the test canister. Radiation sampling aircraft and helicopters equipped with motion picture and television cameras maneuver to be in the proper position at 0 time. Members of the test staff are at their stations in the command room.
20 seconds. 15 seconds.
There is little tension. Many of the men are veterans of more than 300 underground tests conducted from this building.
5, 4, 3, 2, 1, 0 time.
There is little to be seen at ground zero during a detonation. The Earth jumps a little and dust clouds rise. Deep underground, billions of atoms have released tremendous energy through fission or fusion. The material in the device and the Earth around it is vaporized. In less than a millionth of a second, the all-important electrical signals, which will indicate to scientists the results of this test, are transmitted to recording devices above ground. Below, the explosive energy compacts the Earth to form a large spherical cavity. Radioactive products are captured in a layer of molten material which forms around the cavity. As the cavity cools, the molten material falls to the floor and solidifies into a puddle containing most of the radioactive products from the detonation. Valuable data on performance of the test explosive will be provided when samples of this material are recovered later. As the cavity cools further, pressure decreases. Earth and loose rocks fall from above into the void. Ordinarily, the chimneying continues until the Earth at the surface sinks and a saucer-like subsidence is formed, usually within a few minutes, but sometimes not for as long as hours, days, or even months. The command room receives and charts radiation level reports from the telemetering instruments surrounding Ground Zero and from aircraft which fly over the area. Normally, only background radiation levels are indicated. Weather and radiation monitoring personnel remain at their off-site locations until closer aerial surveys and initial re-entry teams verify that there has been no leakage of radiation. Only then are they released by the test controller. Special drilling rigs are set up and soon go to work to obtain samples from the puddle. Drilling operations proceed swiftly with crews working around the clock. Precautions are taken against release of radioactivity to the atmosphere. Blowout preventers are used to contain the entrapped radioactive gases which might otherwise be released at the surface. Samples of the puddle material are required for radiochemical analysis. The radioactive samples are handled carefully and quickly packaged in shielded containers for shipment to the test laboratory. Analysis of the recovered samples and of electrical impulse recordings made at the time of detonation provide scientists with the knowledge of how the explosive device performed. The underground nuclear testing program at the Nevada test site is only a part of the vast research effort of the Energy Research and Development Administration. The Nevada Operations Office also supports energy research programs in other locations, such as the development of natural gas deposits and the investigation of geothermal energy sources in cooperation with industry and other government agencies. Programs conducted by the Energy Research and Development Administration's Nevada Operations Office are essential to our national security and may help to provide energy for our nation in the future.